What if the moon wasn't always the silent, unchanging orb we see today? For billions of years, our closest celestial neighbor was a fiery world, erupting with volcanoes on an epic scale. We're about to unlock the secrets of this explosive past, all thanks to some incredible rocks brought back to Earth. Forget everything you thought you knew about the moon's quiet history. These aren't just any space rocks, they're time capsules from a period of intense volcanic activity that reshaped our lunar neighbor. Prepare to be amazed as we reveal how these ancient samples paint a picture of a truly dynamic moon. Imagine holding a piece of the moon that could tell you stories of ancient lava flows and colossal eruptions. That's exactly what lunar rocks allow us to do. Join us as we journey back in time, using these precious samples to uncover the moon's fiery, volcanic past and understand how it became the celestial body we know today. In the soft hush of a night that seems almost to lean closer with curiosity, the moon hangs above like an ancient lantern, its glow muted yet full of silent stories waiting to be unwrapped. If you listen with the kind of patience that comes only when the world grows slow, you might sense that the moon has been quietly keeping memories in the cool grain of its stones. These memories are older than any mountain on Earth, older than the oceans that now whisper against our shores, and they drift around the moon like invisible dust shaped by time. Each rock is a chapter, each grain a sentence, each mineral a softly breathing fragment of the world the moon once was. Much of what we know about that distant companion comes not from grand cataclysms but from these small, serene witnesses, holding their place in the universe without saying a word. The lunar stones offer their stories not with sound but with patience, as though they understand that the human mind needs gentleness to sink deeply enough to comprehend something so vast. When scientists first touched those stones brought back from the Apollo missions, they spoke about an unexpected stillness in them, a quiet that felt older than any silence on Earth. These rocks, forged in volcanic heat billions of years ago, cooled slowly in the kind of peaceful darkness that only a world without wind can provide. And now, as you drift gently toward sleep, imagine letting your thoughts settle into that same stillness, letting the moon's memories drift toward you like tiny glimmers of understanding rising through calm water. The moon's surface, scarred yet serene, is a mosaic of forgotten heat. Basalt plains stretch across it like frozen seas, each one a remnant of volcanic eruptions so slow-moving and steady that they seem more like breaths from a slumbering world than violent bursts. These ancient plains whisper of a time when the moon was alive with molten motion, glowing under a crust too thin to contain the quiet fury beneath. Though that heat has long faded, a trace remains in the mineral fingerprints etched into every stone, warm stories left behind by a planetary body that once pulsed with energy. As you picture those landscapes, let yourself drift deeper into their gentle, patient echoes. Imagine holding a piece of the moon, cool and grainy, its surface shaped by collisions with dust-sized meteoroids that have tapped its skin for billions of years, like soft knuckles knocking politely on a door. These tiny impacts are not violent in the way great craters are. Instead, they are subtle, persistent reminders of the cosmic quiet that envelops the moon. They leave behind glassy beads and powdered regolith, material so fine it drifts like ancient talcum, each particle shaped in slow motion by time itself. If you run your drifting imagination over its surface, you can almost feel how the moon has been patiently sculpted. The rocks also carry within them traces of solar wind, charged particles streaming from the sun, embedding themselves into the moon's unprotected soil. Over eons, these particles whispered their stories into the stones, adding a faint chemical memory of the sun's breath to the moon's own tale. Earth never kept such memories so clearly. Our atmosphere washes them away, our winds erase them, our rains overwrite them. But the moon, with its stillness and silence, preserved every subtle imprint, and through those imprints, we learn not only about the moon but also about the broader solar system that cradles us. When researchers study the isotopes within lunar rocks, they discover clues about the moon's ancient magma oceans, vast, glowing expanses that once covered its surface like a molten sea under a young and restless sky. As those oceans cooled, minerals separated like dream fragments settling into different layers, each layer forming new stories, new memories locked into crystalline shapes. By analyzing those minerals, we trace the moon's earliest childhood, a time when it was still shaping itself, still learning what it meant to be a satellite of Earth. Those stories unfold slowly, and tonight, as you relax further, let them unfold for you too. And then there are the anorthosites, pale, shimmering rocks that make up the highlands. These stones are among the oldest solid surfaces in the entire solar system. They formed when lighter minerals floated to the top of the moon's early magma ocean, cooling gently into the bright, reflective crust we now see glowing in the night sky. Holding an anorthosite is like holding the moon's first breath as a solid world. It is a fragment of beginnings, a reminder that even the hardest surfaces were once glowing liquid, slowly calming down into the quiet companionship the moon offers Earth today. Some lunar rocks tell of impacts so ancient and immense that their heat reshaped entire regions. These collisions created melt sheets, oceans of rock briefly liquefied, then frozen forever into new forms. The surfaces you see when you look up at the moon's face, the dark maria and bright scars, are not random decorations, they are the fossils of unimaginable moments. Yet even those catastrophic events carry a strange softness now, muted by time, as though the moon has learned to cradle its history rather than display it boldly. The moon's stones reveal that it once had a magnetic field, faint but present, strong enough to leave signatures locked inside certain minerals. A magnetic field means movement, heat, a stirring interior. Though the moon eventually quieted, the memory of that inner motion still lingers in the crystals that aligned themselves with its ancient magnetic lines. It's as if the rocks remember the hum of a heartbeat that has now gone silent. And just as your breath slows as sleep approaches, the moon's core slowed, cooled, and grew still. Some of the most delicate stories come from tiny volcanic beads, glass droplets formed when gas-rich magma erupted in shimmering arcs, cooling instantly as they flew into the vacuum. These beads are like frozen sparks, remnants of fiery fountains that once painted the moon with brief moments of glowing motion. Their colors, subtle and varied, reveal differences in chemistry and temperature, allowing scientists to reconstruct the nature of eruptions that ended billions of years before humans ever looked skyward with wonder. As we read these quiet stories through spectroscopy and microscopy, the moon becomes less of a distant orb and more like an old library of crystalline pages, each waiting to be read. The rocks show how the moon's crust thickened, cracked, cooled. They reveal how its interior slowly lost heat, how its volcanic chapters closed one by one until only silence remained. And in that silence, the stones settled into their places like books on untouched shelves. Even the dust, the fragile, powdery regolith, holds memories in the form of tiny agglutinates, small lumps of melted and fused grains created by micrometeorite impacts. Each agglutinate is like a time capsule, containing bits of rock, glass, and solar wind gases trapped within its structure. These tiny clusters reveal cycles of melting, breaking, and reforming, all happening in slow motion over billions of years. Nothing on the moon erases these processes, they simply accumulate like layers of soft, cosmic breathing. The moon's surface temperatures swing wildly between searing heat and bitter cold, and these fluctuations slowly fracture rocks into smaller fragments. In that sense, even temperature itself becomes a sculptor, carving the moon's memories into finer and finer detail. As stones crack and turn to dust, they create new surfaces for solar wind to write upon, ensuring that every era leaves something behind, however subtle. We learn from the rocks that the moon is not merely a companion but a witness, one that watched Earth grow seas, continents, life. Some lunar soils contain tiny fragments thrown from Earth by ancient impacts, meaning that pieces of our world once traveled outward and landed gently on the moon. In that way, The Moon carries a faint memory of Earth itself, a quiet reminder of the deep connection between the two worlds. Other lunar stones tell of the Moon's long, airless nights, during which cosmic rays penetrate deeply into the ground. These rays alter the atoms within minerals, changing their structure in ways that scientists can measure, almost like tiny timestamps left by the universe. The stones become records of cosmic weather, gentle in appearance but rich with history. Over unimaginable stretches of time, the Moon gathered materials from comets and asteroids as well, embedding traces of distant worlds into its soil. These fragments reveal the chemical diversity of the early solar system, preserved in pristine form because the Moon has no atmosphere to break them down. In this way, the Moon becomes a museum, holding exhibits from across the cosmic neighborhood. The oldest lunar zircons, tiny, resilient crystals, hold within them some of the most precise ages ever measured. These minuscule grains survived conditions that would have erased most other minerals, allowing researchers to peer back into the Moon's earliest formation moments. Their endurance adds a steady, reassuring note to the Moon's stone memory, like the slow ticking of a cosmic clock. The Moon's rocks also reveal how its surface was shaped by the late heavy bombardment, a period of intense impacts that churned and melted its crust. These events left behind breccias, rocks formed from fragments fused together by heat and pressure. Breccias resemble mosaics created by ancient hands, each piece a shard of a different story, fused together by the universe's own quiet, relentless artistry. Some stones contain vesicles, tiny bubbles trapped when lava cooled quickly. These bubbles whisper of gases once present in the Moon's interior, remnants of a time when its surface was still warm enough to release subtle breaths into the vacuum. Though the Moon no longer exhales, these bubbles preserve the memory of that ancient motion. Even the distribution of elements like titanium, iron, and rare earths tells stories of differentiation and cooling, revealing how the Moon's interior evolved. Each concentration pattern is like a trail leading back through time, guiding scientists through the Moon's internal architecture, one quiet step at a time. As we gather all these memories, the Moon becomes less a mystery and more a companion sharing its quiet truth through stone and dust. Every mineral, every crystal, every trace gas offers a small kindness, a glimpse into a world that has carried its history without altering it, without rushing, without forgetting. And now, as you drift into the gentlest edges of sleep, imagine the Moon watching over Earth as it has for billions of years, its stone memories glowing softly in the silence. The stories it carries are patient, deep, and unhurried, perfect companions for a mind settling into rest, guided by the quiet invitation of a world that has always known how to hold still. In the earliest hours of the solar system, before Earth had seas, before its sky carried even the quietest shade of blue, the world was still young, hot, and unsettled. The sun glowed fiercely over a swirling disk of dust and molten fragments, and within that restless chaos, Earth was forming piece by piece. Yet it was not alone in those early days. A wandering protoplanet, something roughly the size of Mars, moved through that same space, drifting closer, pulled by gravity into a slow dance with the growing Earth. That dance would soon become the beginning of a story written into every grain of lunar stone. As the two worlds drew nearer, their orbits brought them into a collision trajectory, though neither had any awareness of the profound event that would follow. The impact was not a sudden crack but a monumental merging of momentum, heat, and molten matter. It was a cosmic encounter so immense that it reshaped both bodies. This protoplanet, which scientists now call Theia, collided with Earth in a way that would have looked impossibly bright, like a second sun exploding briefly in the darkness. Yet even in this violence, something gentle would eventually emerge, a companion, a satellite, a quiet witness for ages to come. The collision ejected vast amounts of Earth's outer layers into space, spreading molten debris into an expanding, glowing halo around the wounded planet. This halo moved slowly at first, drifting and separating into threads and clumps like sparks from a great fire. The debris remained suspended, circling Earth in spiraling arcs, each fragment small in the scale of cosmic events but carrying within it the chemistry, the minerals, and the potential to become part of something new. The early Earth glowed a deep, molten red below, illuminating the drifting material like scattered embers. Over time, the debris began to cool, though not in the calm way we imagine cooling now. Instead, each fragment radiated its heat into the emptiness of space, hardening into droplets, shards, and molten lumps that gradually clumped together. Gravity became the silent sculptor, pulling these pieces into larger and larger groups until one dominant mass began to grow, gathering the surrounding debris into itself. This mass was the first form of the moon, still molten, still shimmering, still far from the quiet companion we see today, but already taking shape in its earliest outline. As the newborn moon grew, it orbited closer to Earth than it does now, so close that it filled a huge portion of the sky like a glowing, restless world. Its molten surface churned with heat, glowing with shades of orange and white like a living ember. The Earth below was still recovering from the collision, its surface chaotic, its atmosphere filled with vaporized rock. Yet the gravitational pull between the two bodies began to stabilize, forming a relationship that would shape tides, seasons, and the rhythm of life billions of years later. The moon's early ocean of magma stretched across its entire surface, deep and bright, roiling under the pull of Earth's gravity. This ocean moved in slow waves, rising and falling under gravitational forces so intense that they reshaped the molten crust again and again. Over time, lighter minerals floated upward like soft foam, forming the beginnings of the moon's crust. These floating minerals would eventually cool into pale anorthosites, the bright highland rocks that today give the moon its luminous glow when sunlight brushes across it. Meanwhile, heavier minerals sank deeper, forming layers that recorded the moon's earliest internal structure. As the crust thickened, the magma beneath began to separate into different chambers, each carrying unique mineral compositions. These chambers would someday erupt, forming volcanic plains that historians billions of years later would call the Lunar Maria. But for now, everything remained in motion, cooling, shifting, settling into long-term stillness. As hundreds of millions of years passed, the moon began to cool significantly. The once glowing surface dimmed to dull reds and then to solid grays. Early impacts from wandering rocks punctured its surface, leaving craters that hardened into permanent scars. Unlike Earth, which had weather, wind, rain, and tectonics to heal its wounds, the moon had no such comforts. Every mark would remain, keeping the history of early impacts preserved like delicate etchings in old stone. During this time, Earth and Moon were locked in a gravitational interplay that pulled at both bodies, slowing Earth's rotation and gradually pushing the Moon outward into a wider orbit. This slow drift continues even today, a reminder that their connection is dynamic rather than frozen, always gently shifting with the quiet persistence of celestial motion. The Moon's interior continued to evolve as heat escaped into space. Radioactive elements decayed, adding faint warmth to the deeper layers, while the outer crust grew more rigid. Volcanic activity persisted beneath the surface, building pressure in pockets of molten rock. When those pockets finally erupted, they created vast lava flows that filled ancient basins, smoothing them into the dark plains we observe today. These eruptions were not explosive but gentle, broad, and patient, spreading through cracks like illuminated rivers before cooling again. Over time, the moon's volcanic activity slowed as its interior cooled further. The magma chambers hardened, the eruptions ceased, and the moon entered a long, quiet phase of geological stillness. Its surface, once active and shifting, became a canvas upon which meteoroids and cosmic dust would write the next chapters of its story. The early solar system remained turbulent, and the moon received countless impacts, large enough to carve enormous basins and small enough to pepper its surface with fine craters. These impacts reshaped its crust, mixing layers, creating breccias, and scattering fragments that revealed the internal composition. Each strike added another stroke to a portrait billions of years in the making. As the impacts continued, fragments from Earth, asteroids, and possibly even other distant bodies became embedded in the lunar soil. These foreign pieces quietly merged with the Moon's own minerals, creating a rich geological archive. In this way, the Moon became a keeper not only of its own past but of pieces of the broader solar system's early history. Meanwhile, the cooling crust cracked and shifted slightly, though not in the dramatic way Earth's plates do. Instead, the Moon's movements were subtle, like the slow settling of old wood. These shifts created wrinkle ridges and small faults that still stretch across its surface today, gentle reminders that even a quiet world once moved with internal warmth. As billions of years passed, the solar system calmed, and the Moon entered its present state airless, silent, immobile. Yet in this stillness, it preserved the memories that Earth lost to erosion, oceans, and tectonic churn. Every crater, every bead of volcanic glass, every mineral grain remained where time placed it, waiting for future observers to listen to the stories etched into their structure. When human eyes first looked at the Moon through telescopes, they saw patterns and shadows without knowing the truth behind them. They imagined seas, continents, even mythical beings. But the real story, the true beginning, was hidden in chemistry and mineral layers born from that ancient collision. It was a story waiting to be uncovered by hands that would someday reach across space. With the arrival of spacecraft, we learned to read the Moon in a new language. Instruments measured isotopes, compositions, and grain textures, revealing the Moon's origin in unprecedented detail. Each sample brought back to Earth whispered hints of the collision that birthed it, confirming theories and deepening our understanding of the early solar system. Today, when we look at the Moon rising over quiet landscapes, we see more than a pale disk hanging in the sky. We see a companion forged from Earth's own body, a world shaped by fire, cooled by time, and preserved by stillness. We see the result of a cosmic event that transformed chaos into companionship. And as this awareness settles into the edges of your mind, it becomes easier to sense the Moon's quiet presence not as something separate, but as something deeply connected to our own story. The Moon's birth reminds us that creation can rise from upheaval, that long-term calm can follow early turbulence, and that even the most transformative events can leave behind something gentle. In the Moon's rocky memory, the story of its birth unfolds not as a moment of destruction but as the beginning of a partnership that has lasted almost the entire history of Earth. And now, as your thoughts drift like the early debris that once circled the young Earth, you can feel how every piece eventually found its place. How every movement, however chaotic, led to the formation of something enduring. How silence grew from fire, and how calm emerged from collision. The Moon's origin is written in stone, but felt best in the quiet spaces between breaths. Even now, the Moon continues its slow outward drift, carrying the memory of its creation while circling the world that gave it life. Their bond, born in fire, shaped by gravity, preserved by time, is one of the most enduring relationships in the solar system, a steady rhythm, a glowing reminder, a companion born from the very place it now watches over. And as you slip deeper into rest, imagine the early sky filled with the light of molten Earth and Moon, two worlds forming side by side, finding balance after chaos. That beginning still echoes softly through the ages, through stone, through dust, through the peaceful glow that reaches your eyes tonight. When scientists first explored the Moon's surface through returned samples, orbiters, and gentle robotic visitors, they began to notice that the stones lying across that quiet world seemed to fall naturally into three great families. Each family carried its own mood, its own tone, and its own manner of whispering history. Together, these families created a soft geological symphony, revealing how the Moon cooled, cracked, erupted, and endured. And now, as you settle deeper into stillness, Imagine these families not as technical divisions but as characters in the moon's long, gentle memory, each one offering a slightly different lullaby of time. The first family, the anorthosites, came from the highest and oldest regions, the lunar highlands. These pale rocks shimmer softly under sunlight, reflecting much of what touches them and giving the moon its bright, almost ghost-like glow. They are ancient, dating back to the time when the moon was still a glowing sphere of magma. As lighter minerals crystallized and floated upward, they cooled into the highland crust. So when you look at the bright patches on the moon from Earth, you are seeing the frozen surface of the solar system's early days, preserved with almost maternal gentleness. These anorthosites carry within them stories of the primordial magma ocean. Their minerals, especially plagioclase feldspar, formed in an environment where heat and silence merged into one. Scientists examining the crystals find traces of slow cooling, whispering that the early moon was patient, taking its time to solidify. In that slow cooling, tiny distortions formed within the crystals, signatures of the moon's shrinking, cracking, and relaxing into its final shape. The rocks hold on to this ancient tension the way old wooden beams sometimes sigh as temperatures shift, as though remembering the long journey from fluid fire to solid calm. The second family, the basalts, tell a very different story. These rocks formed billions of years after the anorthosites, during an era when the moon experienced widespread volcanic activity. Unlike explosive volcanoes on Earth, lunar eruptions were gentle, releasing broad rivers of lava that flowed into vast basins created by ancient impacts. These flows cooled into smooth, dark plains that today form the Maria, the seas that early astronomers mistook for water. In reality, they are plains of frozen fire, dark enough to give the moon its famous contrasting face. Basalts carry the memory of deep interior heat that persisted long after the moon's crust solidified. They reveal the composition of the mantle, the temperature at which the lava erupted, and the slow conditions under which the molten rivers cooled. Some basalts contain tiny metallic grains or shimmering flecks that reflect the conditions of their birth. Others hold vesicles, little bubbles trapped when gases escaped. These bubbles are whispers of the moon's faint breath during its volcanic youth, captured forever inside a cooling stone. Within these basalts, scientists find variations that reveal the moon's complexity. Some basalts are rich in titanium, giving them a unique bluish tint when mapped by spectrometers. Others are low in titanium, showing different origins and melting histories. Even though the moon looks simple to the unaided eye, these basalts remind us that beneath its calm exterior once flowed intricate patterns of heat and chemistry, like quiet music that continued long after the initial creation event. The third family, the breccias, formed not from fire but from impact, those countless collisions that shaped the lunar surface into a mosaic of scars and fractures. Breccias are assembled from fragments of older rocks, fused together through the immense heat and pressure of meteorite impacts. They are like patchwork quilts, each piece coming from a different time or layer, yet bound together into something new. These rocks are the storytellers of the moon's surface, holding memories of both destruction and renewal. Breccias come in many forms. Some retain their fragments clearly, like broken shards frozen mid-motion. Others have been melted into smoother textures, still carrying the essence of their origins but softened by heat. Some even contain glass formed by the intense energy of impacts, glass that cooled instantly, preserving the moment of collision like a flash photograph in solid form. These glasses sometimes appear as beads, sometimes as thin coatings, sometimes as transparent pockets within the breccia's body. What makes breccias especially soothing to imagine is how they show the moon's resilience. Each fragment represents something that was broken, scattered, and then gathered again into a new form. It is a slow, cosmic kind of healing, not through regeneration like life on Earth, but through gentle reassembly. The moon does not erase its wounds, it rearranges them into something meaningful, something that carries its history openly and quietly. Some breccias formed in the earliest ages of the Moon, during the heavy bombardment period when massive impacts reshaped entire regions. These ancient breccias hold fragments of the Moon's first crust, giving scientists rare windows into the earliest minerals and textures. Other breccias formed much later, showing that impacts continued to shape the Moon long after volcanic activity ceased. Through them, we see that time on the Moon moves not in smooth waves, but in distinct, echoing moments, impacts separated by long periods of stillness. In addition to these three families, scientists sometimes find rocks that combine characteristics of more than one group. A basalt fragment might be locked inside a breccia. A piece of anorthosite might appear within a volcanic glass layer. These combinations remind us that the Moon's history is not neatly divided, but intertwined in the way natural stories often are. The boundaries blur, merge, and overlap gently, forming a geological tapestry rather than a catalogue. Each family of rocks also gives clues about how the Moon cooled internally. The anorthosites show that the crust formed from flotation. The basalts show that the mantle retained heat and continued to melt long after crust formation. The breccias show how impacts repeatedly mixed and remixed the upper layers. Together, they reveal a Moon that evolved slowly, with phases of heat, quiet, chaos, and deep stillness. Even the way these rocks weather over time is different. Anorthosites become pitted and dulled by micrometeorite sandblasting. Basalts acquire tiny glass coatings formed by impact melt splashes. Breccias develop fine textures as their mixed fragments respond differently to temperature extremes. These subtle changes over billions of years turn the surface into a soft, grey mosaic that holds the Moon's memory gently and evenly. Another quiet detail lies in how these rocks record exposure age, how long they have been sitting on the surface. Solar wind particles, cosmic rays, and micrometeorites all leave faint traces in the minerals. Some rocks have been exposed for millions of years, others for only thousands. It is as if each stone carries not only the memory of its formation, but also a diary of its time lying under the open sky. When humans collected samples during the Apollo missions, they brought back representatives from all three families. These stones, carried across space in small containers, brought with them billions of years of quiet patience. Scientists describe moments of or when holding them, knowing that these were not just rocks, but records of entire planetary epochs. The stones conveyed stories far older than any fossil on Earth, older than mountains, older than oceans, older even than many elements of our atmosphere. Today, robotic missions continue to identify new variations and subtle chemical signatures within these rock families. Each discovery adds another line to the Moon's story, refining what we understand about its origin and evolution. And with each line, the Moon becomes not a barren world, but a place with depth, memory, and gentle, geological emotion. If you imagine kneeling on the lunar surface, brushing your fingers across the powdery regolith, you might feel the differences between these rock families through texture alone. The anorthosites would feel pale and crystalline, the basalts heavier and smoother, the breccias rough and varied. Each one invites a different kind of reflection, a different rhythm of thought, a different sense of time. Together, these rocks form a complete narrative. The anorthosites tell the story of beginnings. The basalts tell the story of transformation. The breccias tell the story of endurance. And the Moon, quiet as it is, holds all three with the same calm acceptance, allowing the stories to exist side by side without conflict. As you drift now toward deeper rest, imagine these three families arranged across the Moon like gentle chapters of a long, soothing book. No rush, no urgency, only the quiet patience of minerals formed in fire, shaped by impacts, preserved by silence. The Moon has carried them for billions of years, and tonight, it shares them with you in the softest possible way, as though offering a small piece of its eternal calm. When we look at the moon with unaided eyes, even from the soft comfort of a quiet night, we notice the great dark patches spread across its face like serene lakes caught in permanent shadow. These dark regions, called Maria, meaning seas, are not seas of water but ancient plains of cooled lava. Yet despite their fiery birth, they now lie in deep stillness, offering a sense of calm that stretches across billions of years. Their smooth surfaces, darker than the highlands around them, cradle the history of a world that once pulsed with molten motion but now rests in silence. These dark plains were born long after the moon's crust first solidified. Massive impacts bombarded the lunar surface during the early solar system, carving out enormous basins so deep and wide that they left the crust fractured and weakened. 4 million years after these impacts, the moon's internal heat lingered, pooling in pockets beneath the crust. When those pockets eventually found pathways to the surface, lava seeped upward through fractures like warm breath escaping into cold air, spreading slowly across the basins left behind. Unlike the dramatic volcanic eruptions on Earth, where lava can burst upward with force and throw ash into the sky, the moon's eruptions were calm and unhurried. With no atmosphere to contain or influence them, the molten rock flowed across the surface in broad, smooth waves. The lava spread for hundreds of kilometers, covering older terrains with a dark, steady sheet. This flow created the mare basalts, dense, fine-grained rocks rich in iron and magnesium. Even after billions of years, their color remains distinct, giving the moon its iconic dual tones. As the lava flows cooled, they formed long, shallow plains that settled like warm ink into the basins. The cooling was slow, influenced by the vacuum of space and the absence of water or air to carry heat away. Crystal grains grew tightly together, forming basalts with subtle variations that scientists can identify today. Some cooled faster, forming tiny crystals almost invisible without microscopes. Others cooled more gradually, allowing larger crystals to develop silent records of temperature and time held inside the stone. The Maria basalts also carry within them the memory of volcanic channels and tubes, paths through which lava once moved. These channels sometimes collapsed, leaving behind sinuous rills that snake across the dark plains. To the eye, they resemble dried riverbeds, but unlike rivers shaped by water, these features were carved by molten rock flowing gently across the moon's surface billions of years ago. Each rill is a reminder that even worlds without liquid water can leave behind fluid paths etched into their landscapes. Some of the mare basalts are enriched in titanium, giving them unique spectral fingerprints that glow with a slightly bluish tint when mapped by lunar instruments. These titanium-rich basalts formed from mantle sources with different compositions than the low titanium varieties. Their presence reveals that the moon's interior was not uniform but layered and diverse. Each pocket of magma had its own history, its own chemistry, its own quiet story waiting to be told. Across these dark plains, tiny beads of volcanic glass still glimmer when illuminated by the sun. These beads were formed when fire fountains, gently erupting jets of molten droplets, sprayed lava upward before cooling instantly into glass. Though the eruptions were subtle compared to Earth's volcanoes, they still released brief, shimmering arcs of heat into the airless sky. The beads they left behind slumber across the mare surfaces, each one a frozen spark from a long-extinguished flame. In some places, lava filled the basins so completely that it buried earlier terrains far beneath its smooth surface. The thickness of these lava flows varies dramatically, from a few meters in thin, stretched-out regions to over a kilometer deep in others. When scientists study the moon's gravitational field, they can detect these thickness variations as faint ripples, showing where lava accumulated most heavily. The very weight of these flows reshaped the crust beneath them, causing slight sinking in some regions and creating subtle structural patterns that only detailed mapping can reveal. The Maria basalts also contained small vesicles, bubbles trapped during eruption. These are clues that even though the Moon lacks an atmosphere, its volcanic eruptions still involved trace amounts of gas. As these gases escaped from the molten rock, they left behind hollow pockets that now rest silently within the stones. In a world where silence dominates everything, these tiny bubbles carry the faintest whispers of the Moon's once warm breath. When the lava finally cooled and solidified completely, the surfaces remained flat and calm for eons. Meteoroids small and large continued to strike the plains, carving new craters into the hardened basalt. Over billions of years, these impacts transformed the once smooth surfaces into soft, worn landscapes covered with powdered regolith. Yet the darkness of the basalt still shows through, defining the mare regions clearly from orbit. Some of the Maria took shape in multiple episodes. A basin might have filled with lava, cooled, and then cracked again millions of years later, allowing more lava to spill upward and cover the older surface. These layered flows reveal that the Moon's interior remained warm longer than once believed. With each episode, the surface expanded slightly, pushing old wrinkles aside and leaving behind ridges where cooling lava contracted and folded. These wrinkle ridges now stretch across the plains like the lines of an unfurled map. The Maria also contain craters within craters, showing a long sequence of events: impacts that struck before the lava flows, impacts that struck afterward, and impacts so old their edges have softened from countless microcollisions. In these overlapping craters, scientists find a timeline etched directly into stone, as if the Moon carefully arranged its memories in layers of shadow and depth. One of the most fascinating aspects of the mare basalts is how they reveal the Moon's internal evolution. Chemical signatures show that as the mantle cooled and changed composition, the magma it produced changed as well. Early basalts differ noticeably from later ones, suggesting that the Moon's interior was slowly transforming, settling, separating, and aging quietly beneath the crust. These changes would never have been visible on the surface if not for the rocks left behind. Despite their dark appearance, the Maria are incredibly reflective of the Moon's volcanic past. They serve as immense canvases upon which the Moon's thermal history is painted with broad strokes. When scientists analyze their mineral content, pyroxenes, olivines, ilmenite, they can reconstruct temperatures, pressures, and melting depths with remarkable precision. Each mineral crystal is a note in a long, slow symphony composed by a cooling world. During the Apollo missions, astronauts walked across these mare plains and collected basalt samples that still carry warmth from their ancient origins, not physical heat, but geological memory. Many of these basalts contain magnetic signatures, tiny alignments of minerals that reveal the Moon once had a magnetic field, though far weaker than Earth's. This suggests that the Moon's core was once active, generating faint magnetic lines that the cooling basalts locked in place like quiet echoes from a fading heartbeat. The Maria form only about 16% of the Moon's surface, but they dominate the near side we see from Earth. This asymmetry hints at differences between the two hemispheres, differences rooted in crust thickness and heat distribution. The far side, with its thicker crust, resisted volcanic resurfacing, while the near side, with thinner crust, allowed lava to flow more freely. So when we gaze upward from Earth, the side we see is the one where the Moon opened itself to volcanic transformation. And yet, despite their fiery origins, the Mare Plains are some of the most tranquil places imaginable. There is no sound, no wind, no movement except the slow drifting of dust under the faint push of charged particles. Standing on one of these plains, if you could, would feel like standing inside time itself, surrounded by frozen echoes of ages when molten rivers shaped the land beneath your feet. Many Maria basalts also contain elements that have helped scientists determine the Moon's age. Radioisotopic dating reveals that the Maria formed in waves between about 3.9 and 3.1 billion years ago, with some younger flows extending to 1.2 billion years. These ages tell us that the Moon's volcanic life was long, lingering. quietly even after the most dramatic early events had ceased. As dust settled over the basalts, tiny particles carried by solar wind began embedding themselves into the surface grains. These solar wind particles reveal the chemical fingerprint of the ancient sun and offer clues about the changes in solar activity over billions of years. The basalts, with their dark, dense surfaces, capture these particles in a way that makes them valuable archives of solar history. Craters like Tycho and Copernicus sit partly on the Maria, their bright ejecta spreading across the dark plains like pale feathers. These contrasts show the relative youth of these craters compared to the basalts beneath them. The bright rays cut across the dark plains like fresh strokes painted over an ancient canvas, sharper, cleaner lines layered over softer, older ones. If you imagine drifting above the moon in slow motion, watching the Maria stretch across the surface like calm, dark sheets, you can feel the quiet endurance of these lava seas. They speak not of violence but of persistence, heat rising, spreading, cooling, and eventually yielding to silence. Their vastness is not overwhelming but soothing, like an endless field of still water frozen under the touch of time. As you sink deeper into rest, picture these plains not as remnants of ancient fire, but as places of serene permanence. They are the moon's great exhalations, released long ago and left to cool under the star-filled sky. And now they wait, dark and steady, carrying the memory of molten rivers beneath a blanket of eternal calm, quiet seas that hold the soft, unbroken rhythm of a world that once glowed but now rests in peaceful shadow. How a rock remembers begins in the silent glow of molten beginnings, where heat once ruled the moon's surface and every drop of glowing liquid carried within it a story waiting to cool into firmness. In that young era, before the plains had hardened and before the highlands had fully risen, the moon was a restless world, shimmering with heat from constant impacts and erupting lava. As the molten pools slowly began to surrender to the coldness of space, they solidified in layers, and each layer formed crystals that locked tiny bits of ancient time inside them, like whispers pressed into stone. These crystals became the moon's quiet memory, small, shining minerals arranged in patterns that reveal how hot it once was, how swiftly or lazily it cooled, and what ingredients drifted within its interior. When the world was still new. The process of forming these crystals is almost like a gentle, patient breath of the moon itself, slowing down enough to let structure form. When lava cools quickly, its crystals stay small, too rushed to grow in their full shapes. But when cooling slows, the minerals have the luxury of expanding into beautiful, visible forms that scientists can later read as though they are letters from a long-lost era. Each crystal forms depending on temperature, pressure, and chemistry, so when a rock is cut open, the shapes inside are not random, they are carefully etched signatures of how that molten moment unfolded. These shapes reveal whether the rock cooled at the surface under open skies or deep within the moon's crust where warmth held on for longer, allowing crystals to bloom slowly and fully. Inside lunar basalts, for instance, crystals of pyroxene and olivine shimmer in tiny patterns like sleepy constellations. In some samples, you find long, slender crystals showing that the cooling happened gently, without sudden changes. In others, the crystals appear more chaotic or fragmentary, revealing a cooling process disrupted by impacts or by being suddenly thrust upward from deeper layers. Every arrangement of crystal is a diary entry of the moon's hidden thermal rhythms, telling of the heat that once pulsed through its interior like a calm, ancient heartbeat. Scientists study these minerals not only to understand composition but to hear the slow echo of how the moon's interior once breathed. Even the colors of these minerals carry memory. The darker shades in mare basalts point to iron-rich crystals, letting researchers know that deep volcanic processes fed those lava seas long ago. Lighter patches hint at different mineral mixes, showing how varied the moon's inner furnace once was. These subtle shades appear like faint moonlit gradients across a rock's surface, offering one more layer of the story for those patient enough to read it. Over time, cosmic rays, and the harsh vacuum of space add tiny marks to the surface, giving each rock its own weathered face. But beneath that weathering lies the original crystalline arrangement, protected like a secret beneath the years. When scientists bring these rocks back to Earth and examine them under microscopes, it's as though they are leaning close to hear the faintest whispers from billions of years ago. They see not just crystals, but timelines, the order in which minerals appeared as the lava cooled, which ones grew first, and which ones formed later as temperatures fell. These sequences reveal how quickly the lava spread, how thick it was, and how deep the source magma had been within the moon. Each rock is a slow, patient storyteller, offering its history not in words but in silent, glittering geometry. Some lunar rocks also hold trapped gas bubbles, little pockets where tiny crystals form around empty spaces. These bubbles can show how gases escaped from molten rock or became sealed in as cooling progressed. If the rock cooled on the surface, gases might escape freely, leaving behind only faint traces. But if cooling happened more deeply, those gases sometimes got trapped, creating smooth, hollow beads or intricate internal shapes that preserve the moment of solidification. These bubbles, though small, carry enormous significance, like soft footprints left in still warm soil. The larger crystals found in lunar highlands rocks tell an even slower story. These rocks formed not from erupting lava at the surface, but from deep within the moon's early crust. There, cooling could take thousands or even millions of years, allowing minerals to grow in broad, shimmering patterns. The anorthosite in the highlands is full of feldspar crystals that reflect pale shades, giving those regions their bright appearance. These feldspar crystals grew when the moon's early magma ocean cooled so slowly that minerals floated and sank in calm, ancient layers. When you look at one of these rocks, you are seeing the memory of the moon's very first cooling process, when its outer layer solidified into the shell we see today. Even the absence of certain minerals can offer memories. Some rocks cooled so quickly that crystals had no time to form, leaving behind glassy fragments, smooth and dark. These fragments often come from meteor impacts that melted the surface for mere seconds before suddenly freezing again. In these cases, the rock remembers not the long, slow cooling of lava, but the sudden flash of heat and pressure delivered by something falling from space. These glassy pieces show the chaotic side of lunar history, moments of violence contrasted with long ages of quiet cooling. Together, crystals and glass create a layered record, almost like pages of a book written over billions of years. Scientists have learned to decipher these pages by comparing shapes, sizes, and patterns. A larger crystal means more time. A fragmented one means disturbance. Glass means speed. The combination of all these clues forms a story more detailed than any written chronicle could ever be, because it is built directly from the events themselves, recorded as they happened in the structure of the rock. Some crystals align in neat directions, hinting that the magma once flowed smoothly, perhaps part of a gentle lava stream that moved across the moon's surface long ago. Other crystals sit at odd angles, indicating that the rock experienced turmoil or rotation before it fully hardened. These alignments allow scientists to reconstruct not just temperature conditions but even movement, traces of ancient flows frozen into the rock like soft ripples preserved under glass. As time passed, impacts shattered many of these rocks and fused their fragments together, forming breccias. Inside breccias, crystals from different origins sit beside one another like pieces of a collage. Some crystals show long, peaceful cooling histories, others show quick, fiery births. Together, they create a more complex memory, a memory of collisions, mixing, and reassembly. Breccias remind us that the moon remembers not only creation but reconstruction, healing, and becoming something new from what was broken. Even the tiny inclusions within crystals tell of ancient conditions. Some minerals trapped microscopic bits of melt, sealing them like small fossils of liquid inside solid stone. These melt inclusions are time capsules of the original magma's composition, allowing scientists to determine what ingredients the Moon carried in its early days. They are quiet reminders that even as a crystal grows, it holds pieces of the world it came from, preserving its birthplace inside its expanding boundaries. When crystals form at different temperatures, they create a layered history within a single rock. Some minerals only appear once the temperature falls below a certain point, so their presence shows how far the cooling progressed. Others form early, giving clues about the initial heat. By mapping these minerals, scientists build a thermal timeline, revealing the sequence of cooling events. It is almost as though a rock contains its own map of time, waiting patiently for someone to unfold it. Under polarized light, these minerals shine with colors, pinks, greens, blues, oranges, revealing internal strain patterns and structural details unseen to the naked eye. These colors are not random. They are the rock's memories made visible, showing where it was stressed, heated, or compressed. Scientists rotate the slides gently, watching the colors shift, learning how the rock responded to forces long gone. This dance of color subtly guides them through the Moon's past. Sometimes, a rock's memory also reflects how it interacted with the environment after cooling. Micrometeorites leave tiny pits. Cosmic radiation alters outer layers. These external markings show how long a rock stayed on the surface and how exposed it was. By studying these changes, researchers can estimate how long the rock lay under starlight before being collected. Even the scars a rock carries become memories, marking its long watch under the steady gaze of space. Lunar crystals even preserve chemical signatures that tell scientists whether the magma came from deep or shallow layers. Different depths hold different elements, so the ratios of these elements act like altitude markers. A rock rich in magnesium and iron suggests deep origins, while those with more aluminum speak of surface or crustal formation. These chemical memories reveal how the Moon's interior evolved over time, becoming more layered and distinct. Some lunar rocks remember tides of heat from nearby impacts. When an impact occurs, surrounding rocks can be reheated, partially melting and recrystallizing. These recrystallization zones show where the heat touched and how far it traveled, like faint echoes of an explosion still visible billions of years later. Through these, scientists understand how energy moved through the lunar crust and how the surface responded to each collision. Other rocks contain zoning within crystals, areas where mineral composition shifts as cooling conditions change. These zones form like growth rings in a tree, each representing a different stage of the cooling process. Sometimes the zones show sudden changes, hinting at abrupt disturbances or shifts in magma chemistry. Other times, the zones transition smoothly, indicating long, uninterrupted cooling. Reading these zones is like tracing the mood of the molten rock, feeling its slow transition from chaos into calmness. Every crystalline memory adds to a broader tapestry that scientists piece together. By examining rocks from different regions of the Moon, they compare cooling histories and reconstruct volcanic events that occurred independently but overlap in time. These comparisons reveal how the Moon's volcanism evolved, which regions cooled first, and how heat beneath the surface gradually diminished. Rocks become chapters in a story, each chapter adding detail to the Moon's long cooling arc. Some rocks remember being part of a lava lake, where surface cooling formed thin crusts that broke and reformed as molten material churned beneath. Crystals formed in such environments often show mixed signs, some shaped by slow cooling at depth, others shaped by quick exposure to cold vacuum. This dual memory tells of a dynamic setting, where heat and chill dance together in an ever-shifting balance. Other rocks cooled in solidifying dikes, narrow channels of magma that squeezed upward through fractures in the crust. These rocks experienced cooling from all sides, creating distinct patterns of crystal alignment. Studying these helps scientists locate ancient pathways through which magma once flowed, mapping the moon's internal plumbing. When cooling finishes, the crystals lock permanently into place, forming the finished memory that will last billions of years. From that moment on, the rock becomes a silent witness to time, carrying its record unchanged unless shattered. Many rocks remained buried for eons before being brought to the surface by impacts. Even that burial is part of their memory, for buried rocks escape surface weathering and preserve their crystalline stories more clearly. Eventually, astronauts collected these rocks and brought them back to Earth, where they were gently handled, studied, and admired. Under careful examination, each crystal offered a soft whisper of ancient events, telling humanity about conditions that existed long before Earth itself had cooled fully. These rocks, once silent and untouched, finally found listeners. And now, each time a lunar rock is studied, its memory continues to unfold, giving scientists a deeper understanding of the moon's distant past. Through crystals, cooling patterns, textures, and scars, the rocks share their long journey, a journey of heat, patience, pressure, and time. In their quiet structure, they remind us that memory can take many forms, and sometimes the most enduring memories are written not in words but in stone. Soft Pilgrims, How We Collected Moonstones, begins with the gentle preparation long before any boot touched the lunar dust, when astronauts practiced in quiet fields on Earth, walking slowly inside bulky suits that resisted every movement, teaching their bodies how to move in a world that would offer less gravity but far more silence. They rehearsed bending, lifting, and placing tools with deliberate calm, knowing that each motion on the moon would have to be balanced like a dance performed in slow, floating rhythm. These preparations shaped their minds into patient vessels, ready to gather rocks with respect, care, and a sense of being humble guests in a place untouched since the dawn of time. When the Apollo missions finally carried these travelers into space, the journey itself felt like moving through layers of stillness until the moon came into view like a pale lantern drifting alone. Approaching the lunar surface, the astronauts felt a tremor of awe mixed with the soft hum of machinery, knowing they were moments away from walking on a world where no human hand had ever reached for a stone. That awareness made their hearts slow, not with fear but with reverence, as if they were about to meet an ancient storyteller whose words had waited billions of years to be heard. The descent was quiet, gentle, and disciplined, guided by engines that whispered rather than roared. The first steps onto the moon were delicate, as though the astronauts feared waking something sleeping beneath the light dust. They tested the surface, felt its soft resistance, and let their movements adapt to the reduced gravity, which made each step float a little. Before collecting anything, they let themselves breathe in the silence around them, a silence deeper than anything on Earth. This stillness encouraged them to handle the environment with near-spiritual calm, understanding that even their footprints would remain for ages. Every gesture had weight, even if their bodies felt lighter. Their tools, though simple in appearance, scoops, tongs, bags, and small rakes, were designed with great care for handling delicate stories preserved in stone. Each instrument was shaped to work in gloves thick enough to protect against harsh temperatures but clumsy enough to make precision a challenge. Still, the astronauts moved with intention, practicing a quiet efficiency so that they could gather materials without disturbing more than necessary. They knew that every grain of dust had value, and every rock might hold secrets older than Earth's oldest fossils. Before picking up the first rock, they photographed it from several angles. This small ritual ensured that scientists on Earth would later understand its original resting place, the angle of its settling, and the company it kept among neighboring fragments. These images acted like bookmarks in the moon's long story, preserving the setting before the stone left home. The astronauts performed this step patiently, never rushing, even when mission time was limited, because accuracy mattered as much as collection. Lifting a lunar rock was not like lifting one on Earth. The stone weighed less, but its fragility demanded a slow, careful grip. The astronauts treated each piece as though it were a delicate relic that might crumble if touched with haste. Some rocks were loose and easy to take, while others were partly embedded, requiring gentle digging with a scoop. With each extraction, the astronauts kept their motion steady, knowing sudden shifts could cause dust to float up unpredictably, sometimes sticking to their suits like soft gray memories. Once collected, each rock was placed in a special sample bag labeled with quiet precision. The bags were simple but essential. They protected the stones from contamination, preserved their arrangement, and ensured that when the samples returned to Earth, scientists could connect each piece to its lunar location. In some missions, larger rocks were placed into metal containers and sealed to preserve even the original atmosphere around them. This attention to detail transformed the act of collection into a kind of gentle ritual. Walking across the surface, the astronauts noticed patterns, rocks clustered near craters, glass beads glimmering faintly, dust spread like powdered shadows. As they moved, they observed without disturbing more than necessary, learning from the landscape even as they collected from it. They were not just gatherers but listeners, trying to sense the quiet character of each region, letting the surroundings inform their choices. Even the act of kneeling became a slow, graceful effort, guided by balance and by the wish not to scatter dust. Sometimes they found rocks that told stories at first glance, breccias formed by impacts, basalts dark as ancient lava, or highland fragments pale and bright. These visually distinct stones were handled with extra care, photographed meticulously, and placed reverently into their containers. The astronauts understood that each unique texture represented a different chapter of lunar history, and they moved as though aware that they were touching pieces of deep time. The collection of drive tubes, long hollow cylinders that were pressed into the ground, allowed the astronauts to gather layers of soil without disturbing their order. This method preserved vertical timelines, showing how dust and tiny rock fragments accumulated over millions of years. Pushing the tube into the surface was a slow, controlled effort requiring strength and gentleness. Once full, the tube was sealed at both ends, capturing a frozen sequence of lunar history that would be studied grain by grain. At times, astronauts paused to simply observe. They looked out over the plains, letting their eyes trace distant ridges and crater rims softened by ages of silence. These moments of reflection grounded them and reminded them why they were there, not as conquerors but as respectful visitors, gathering knowledge rather than claiming territory. The moon's vast stillness seemed to encourage these pauses, offering them space to breathe and appreciate the immensity of what they were doing. Some rocks were collected because they seemed out of place, rounded stones among sharp fragments, or glass droplets among rough dust. These anomalies hinted at past events, impacts, melts, and shifts that shaped the surface. The astronauts, though not geologists by training, learned to recognize these interesting clues through hours of preparation. Their curiosity guided their hands, leading them to pick up stones that whispered of unusual stories. As the astronauts moved across the surface, dust clung to their boots and suits in a way that felt almost alive. The dust was fine, sharp, and ancient, having been ground by countless impacts over billions of years. Though troublesome, this dust also reminded them of the moon's long memory. Every speck had a history. When they bent down to collect samples, they were mindful of how this dust moved, learning its behavior like one learns the temperament of a quiet animal. Communication with Earth accompanied each collection. Through soft static, they described the rocks in simple but careful terms: size, shape, texture, position. These spoken notes provided immediate context for the scientists listening below, turning the astronauts into the moon's gentle narrators. Their words floated between worlds, uniting distant minds in a shared effort to understand a place that had been silent for so long. During some missions, astronauts used a special hammer to break pieces from larger boulders. Even this simple action required patience, because the low gravity made force behave differently. A swing too strong could shift their balance, a swing too weak would leave the rock unbroken. They practiced a middle rhythm, a measured tap-tap that fractured stone without disturbing their stance. When fragments finally came loose, they collected them as though receiving small gifts. The astronauts sometimes brushed dust off rock surfaces to expose textures hidden beneath centuries of fine particles. These careful sweeps revealed sparkles of crystalline mineral or the dull sheen of volcanic glass. Each newfound detail helped them decide whether the stone deserved careful sampling. Their brushes created gentle arcs across the rock, strokes soft enough not to damage, yet deliberate enough to reveal what lay beneath. Even the largest samples were handled with respect. Heavy boulders could not be brought home, but fragments chipped from them were treasured. These big rocks often sat near crater edges, forming natural sculptures shaped by ancient impacts. Standing beside them, astronauts felt the age, the endurance, the sheer patience of stone. Collecting from these giant relics felt like asking permission from the landscape itself. When lunar nights approached or mission time dwindled, astronauts quickened their pace only slightly, still moving with a sense of care. They resisted the temptation to rush, understanding that mistakes could cost precious data or damage delicate samples. Even in moments of urgency, the rhythm of collection remained slow, steady, and thoughtful. The moon seemed to demand such calm. Before ascending back to orbit, the astronauts made a final check of their sample containers, ensuring every seal was in place, every label secured, every bag safely stored. This final inspection felt like thanking the moon for what it had shared, acknowledging the privilege of carrying pieces of its long memory back to Earth. Their voices softened as they read out the numbers, as though speaking in a quiet temple. During liftoff, the collected moonstones rested safely aboard, protected from vibration and heat by layers of care. Even as the spacecraft rose, the samples remained as calm as they had been for eons, unaware that they were leaving their home for the first time. The astronauts, looking down through small windows, knew they were carrying more than rocks, they were carrying stories. Returning to Earth, the samples were greeted with a reverence matching the one used to collect them. Clean rooms, gloved hands, and filtered air awaited their arrival. Yet even with all this technology, researchers maintained the same gentle respect the astronauts had shown. They understood the value of these fragments, not just scientifically but symbolically. They were the moon's soft gift to humanity. In laboratories, the rocks were opened slowly, displayed under bright but sterile lights. Each stone was catalogued, measured, studied, and shared with scientists around the world. These researchers treated the samples not as trophies but as wise elders, each rock containing lessons about lunar formation, volcanic activity, and cosmic impacts. The stones continued to be soft pilgrims themselves, journeying from one mind to another. Though the astronauts had collected only a limited amount, just a few hundred kilograms over all missions, the samples proved far more informative than anyone had imagined. Every gram held meaning. Nothing was wasted. Even dust captured on suit surfaces was studied. The moon's generosity had been quiet but immense, and humanity responded with gratitude, preserving the samples for decades of future study. Decades later, new scientists still examine those same samples using tools undreamed of during the Apollo era. This ongoing care shows that the pilgrimage of moonstones didn't end when they left the moon. Instead, their journey continues, revealing new details as technology improves. Each new discovery feels like a soft continuation of that first gentle gathering. Modern missions now prepare to collect more samples, inspired by the calm patience of those early pilgrims. Plans include robotic assistance, improved tools, and more precise methods of preserving context. But even with advanced technology, the philosophy remains the same: treat the moon with care, gather only what is necessary, and listen to the quiet stories embedded in stone. In the end, The act of collecting moonstones was never about possession. It was about understanding, connection, and humility. The astronauts became temporary caretakers of memories older than life on Earth. Their soft, deliberate motions honored the moon's age and silence, turning the gathering of rocks into an act of respect. And in that respect, they formed a bridge between two worlds, one warm, blue, and alive, and the other calm, grey, and ancient. Through these soft pilgrims and their careful journey, the moon's long-kept stories finally reached our ears. And now, each time we study a lunar rock, we relive that gentle act of discovery, reminding ourselves that knowledge gathered with patience carries a deeper, quieter power, one that endures as long as the stones themselves. The story of time on the moon begins not with sand falling through an hourglass, but with atoms holding tiny secrets, waiting patiently for someone gentle enough to listen. Inside each lunar rock, deep within its crystals, certain atoms are quietly changing, step by step, at a pace so slow and steady that even cosmic winds seem hurried beside them. They decay not with drama but with a soft, predictable rhythm, and this rhythm becomes a whispering clock, a hidden measure of ages long gone by. When scientists hold a moonstone beneath the faint hum of their laboratory lights, they aren't just examining a cold object, they're leaning close to hear that nearly silent ticking. The atoms inside, like parents telling old stories, shift from one form to another, leaving behind traces that speak of how long they have been waiting. In this gentle transformation, one element becomes another, and the balance between the two becomes a kind of diary, showing how long the story has been unfolding. The moon's surface, untouched by weather, oceans, or busy biological life, protects these atomic diaries in a way Earth rarely can. There is no rain to wash away the delicate signatures, no roots pushing through to scramble the traces, no shifting continents to bury or distort the meaning. Everything on the moon sleeps almost exactly where it fell, making its rocks perfect keepers of ancient memories. Scientists find themselves reading pages that remain crisp despite billions of years. But radiometric dating does not rely on sight. It is more like listening to the steady breathing of the universe as it rests. Each radioactive isotope decays at its own unchanging rate, like a candle that always burns at exactly the same speed no matter how the night air moves around it. Uranium becomes lead, potassium becomes argon, rubidium becomes strontium, and in each transformation lies the calm passage of time measured with exquisite precision. Imagine holding a basalt from a lunar mare, a rock born from molten lava that cooled so slowly and quietly that its atoms had time to settle into peaceful arrangements. Inside, uranium atoms began their long journey toward becoming lead, a process that takes far longer than civilizations rise or fade. When scientists measure the ratio between the uranium that remains and the lead that has formed, they are measuring how long ago the lava stopped flowing, locking the clock in place. And in the highlands, where anorthosites gleam like frozen moonlight, different isotopes reveal different timelines. Potassium decaying into argon speaks of extremely ancient ages, pieces of crust nearly as old as the moon itself. Argon, a noble gas, gets trapped inside minerals like soft breath caught in crystal windows. When these rocks are heated again, perhaps by an impact or a volcanic surge, some of that argon escapes, resetting the clock with a gentle puff. If it stays trapped, it becomes a message from the dawn of lunar history. The moon, unlike Earth, has not erased its scars. Every meteorite that struck, every crater that formed, every molten sea that slowly cooled leaves behind a timeline, an event marked in the atoms. Radiometric dating allows scientists to walk backward through these events, step by slow step. It is like strolling through an ancient library where books never fall apart, every chapter preserved in crystalline ink. Each isotope is like a storyteller with its own tempo. Some speak quickly on geological timescales, carbon, for instance, which decays too rapidly to help with ancient lunar ages. Others, like uranium and thorium, speak slowly, calmly, like elders taking their time to ensure every detail is remembered. These long-lived isotopes, with half-lives stretching into billions of years, become the perfect guardians of lunar time. When the Apollo astronauts gathered rocks, they didn't know exactly what timelines were hidden within. But scientists later opened those samples like quiet boxes filled with cosmic lullabies. Inside, they found that the lunar highlands formed more than 4 billion years ago, when the newly formed moon was still glowing with leftover heat. The mare basalts recorded younger but still ancient times, between 3 and 4 billion years ago, moments when molten seas welled up from below and pooled across the surface. A radiometric date is not a guess. It is a mathematical embrace between two states of an atom, measured with delicate instruments that detect even the smallest whisper of transformation. Scientists dissolve tiny pieces of rock, sometimes just grains of mineral, and run them through spectrometers that separate elements like threads pulled from a tapestry. The results paint a picture far clearer than human memory could ever achieve. As the moon cooled, its interior changed, and those changes are written in its rocks. Radiometric dating helps scientists map when the magma ocean crystallized, when the crust solidified, when impacts reshaped entire regions. Each event shows up as a reset or disturbance. In the isotopic clocks, where clocks remain untouched, they reveal peaceful chapters of lunar history. Where clocks were reset, they reveal moments of cosmic drama. Sometimes, scientists find rocks that recorded several events. A crystal may have begun forming in a slowly cooling magma ocean, then later been shattered by an impact, then reheated by lava. Radiometric dating can unravel these layered stories, separating the earliest birth date from the later reshaping, allowing researchers to trace the entire journey of a single piece of the moon across immense spans of time. The beauty of this method lies in its reliability. Isotopes decay with half-lives so fixed that nothing in the environment can alter their pace, not temperature, not pressure, not gravity, not even cosmic radiation. This constancy turns them into perfect timekeepers, immune to the chaos of the universe. They offer calm truth even when everything else is shifting and uncertain. Inside each lunar rock, the atoms have waited patiently for billions of years, undisturbed by storms, oceans, or drifting continents. When scientists measure them, they awaken these ancient clocks, not by altering them but by gently observing the marks they have left. The moon, serene and untroubled, becomes a place where time has kept itself pure. Radiometric dating reveals that the moon formed shortly after Earth itself, a companion born from a colossal impact that reshaped the young solar system. The ages of the rocks confirm this narrative. Crystals that formed in the first 100 million years of the solar system remain preserved in the lunar crust. No other place in the inner solar system gives us such a steady and uninterrupted timeline. Some crystals, such as zircons, are especially good at keeping time. They reject impurities as they form, trapping uranium but excluding lead. This means any lead found inside them later must have come from radioactive decay, making the dating remarkably precise. These beautifully stubborn minerals act like tiny time capsules, locked shut since their creation. The moon's basalts, on the other hand, tell of later activity. Their ages reveal when volcanic outflows welled up to fill basins and darken the surface. These lava flows spread across wide plains, cooled, and set their isotopic clocks. Through them, we learn that the moon was volcanically active far longer than once expected, humming with internal heat long after its surface seemed still. As scientists study more samples, both from Apollo missions and lunar meteorites that found their way to Earth, the clock becomes more detailed. It reveals periods of calm, long stretches when nothing disturbed the surface, and moments of chaos, when impacts or eruptions reshaped entire landscapes. Each rock helps refine the timeline, like stitching threads into a tapestry that grows clearer with every addition. Radiometric clocks also help scientists compare events across different regions of the Moon. For example, they allow researchers to determine whether two far-flung basins filled with lava at the same time or whether one is much older. This reveals connections between volcanic events, internal heat flow, and the Moon's slow cooling across the ages. The Moon's chronology becomes a gentle map of ages, stretching back farther than anything visible to the naked eye. Radiometric dating turns barren plains and jagged highlands into chapters of a vast history book. Craters, once just shapes, become markers of time. Mountains, once only silhouettes, become places where ancient and younger rocks whisper to each other across their boundaries. Long after the solar system formed, while Earth was still reshaping itself with oceans, atmosphere, and life, the Moon carried on its quiet aging. Its rocks absorbed no deep changes after they cooled. When scientists date them, they are reading memories from an era when Earth was unrecognizable. The Moon becomes not only a witness to its own story but also to Earth's earliest chapters. The atoms that decay inside lunar rocks do not hurry. Their pace is determined by physical laws that never waver. This slow, predictable rhythm transforms each stone into a gentle chronometer, a soft-spoken teller of ages that reach beyond imagination. For a world that sleeps beneath sunlight unfiltered by air, these clocks are perfect companions. To date a rock is to touch a moment older than any human thought. It is to reach into a past so deep that no myth, memory, or dream can match it. Radiometric dating becomes a quiet act of listening, scientists holding their breath as the atoms reveal the story they have been carrying since long before Earth's continents drifted or life began to stir. Each time a scientist announces the age of a lunar rock, they are stating not just a number but a slow, cosmic truth. They are sharing a whisper heard from across billions of years, a whisper preserved by silence, by stillness, by a world that never let its memories scatter. The Moon gives its story freely once someone understands how to ask. And so, radiometric dating becomes the Moon's lullaby of time, soft, steady, unbroken. It tells us that even in a world without air or life, memory endures. Rocks hold the past gently, the way a calm sea holds reflections, never rushing, never forgetting. And as we study them, we learn that time is not just something that passes, it is something quietly kept.